Mhm. Okay, so why are we? So last time we discussed about socks. Not elaborately, but briefly, we have talked about in some assignment question what socks are. So basically, socks are discontinuities developed in supersonic flow. So you can actually, I have done some of my works in my PhD regarding socks. So it's a very interesting phenomenon. Socks are everywhere, like when you slam a door, like tadas, it also a sock. There is a sock propagate. Or if you like drop a pebble into a pond, you see tiny little wave propagates. So the pebble pull a force along the water, and there a shock creates. Or more better intense example will be the blast like Hiroshima and Nagasaki, two of humankind's most indigenous events. So they create some shocks. So basically, shocks are discontinued to develop in supersonic flow. It has some finer thickness and near shock viscous terms relevant. Okay, for shocks in steady flows, viscous effect is equal to inertial term approximately. So rho u dot del dot u. Let me zoom in. Rho u dot del u approximately mu del square u. So rho u times du dx is approximately mu times d2u dx2. So no ideal discontinuities in real life. Finite thickness will be mu by u. Okay, so delta. Less viscous fluids, thinner socks. So as the viscosity is less, the sock will be thinner. Faster flow, sharper sock. Sock will be sharp. Now, and you will be centimeter square per second proportional to lambda u average, that is proportional to lambda u RMS proportional to lambda CS. Okay. For shocks in mildly supersonic steady flows in approximately 1. That is neither subsonic neither supersonic. It's basically at the Mach level 1. So initial term approximately pressure gradient term. So rho u du dx approximately dp dx is equal to cc square d rho dx. So then rho u square by delta will be equal to cc square by delta. Will be u is equal to cs. Shock thickness is equal to mean free path. So lambda is equal to, I already told you, delta is equal to this nu by u, which is nu by u average, that is lambda. Because u average is uh, yeah, cs. So yeah, that will be like that. So then that is approximately lambda. So basically, shock thickness will be the mean free path. You know the mean free path. The idea of mean free path is suppose there are two atoms. So two atoms collide, right? So the average distance. So the distance between these two particles before they collide is actually free path. If you consider ensemble of particles, then the average of that distance is mean free path. That is said that within that distance they don't collide, so that they are free to move. So basically shock thickness is approximately mean free path. Okay. From here, nu by u average is lambda. Okay. Shock jump conditions for normal shocks. Rapid stream. So zone 1, this is zone 1. The density here is rho1, pressure is P1, velocity is U1. This is the shock front. And the velocity here is U2. This is zone 2. So rho2 and P2 corresponding density and pressure. So zone 1 is fluid approaches shock front with velocity U1. Pre-shock fluid zone ahead of shock. So pre-shock fluid, this is the zone 1. Zone 1 is the pre-shock. So suppose here the shock front generates a shock front propagate like this side. So this is the shock free zone. That's why called pre-shock, before shock. Zone ahead of shock. This is called ahead. You can think it behind, but actually because it is ahead of shock, shock yet not generated. So ahead of shock. This is zone 2 is downstream where fluid leaves shock front with velocity U2. Okay. This is the post-shock fluid or zone behind shock. Shock passes through fluid to convert supersonic flow to subsonic. Shock passes through fluid to convert supersonic flow to subsonic for normal shock. So mass flux conservation is there. Rho1 U1 is rho2 U2, obviously. All your equation is there. P1 plus rho1 U1 U square is equal to P2 plus rho2 U2 square. Okay. Energy conservation is there. Half U1 square plus omega 1 equal to half A2 square plus omega 2. This is the kinetic energy, potential energy, or internal energy. Kinetic energy also can be bulk motion of energy. This is the similarly for post shock. So omega is equal to gamma by gamma minus 1 p by rho. Okay. So the internal energy can be calculated like this. So from Bernoulli equation, we get that omega is equal to integration of dp by rho, right? So now for barometric fluid, P is equal to root to the power gamma. So dP is equal to gamma root to the power gamma minus 1 d rho. Okay. So then omega will be gamma root to the power gamma minus 2 d rho. But it is gamma by gamma minus 1 root to the power gamma minus 1. Root to the power gamma by rho. Root to the power gamma is P. You can consider here C also, that doesn't matter because C will be just constant. So here again it will be this only. So sorry, omega is equal to gamma by gamma minus 1 p by rho. Okay, that is the internal energy. Shock jump conditions again. Derive rho 1 by rho 2 is gamma minus 1 by gamma plus 1 plus 1 by m square 2 by gamma plus 1. So this will give P1 plus rho 1 U1 square by rho 1 U1 equal to P2 plus rho 2 U2 square by rho 2 U2. Here S1 square is equal to gamma P1 by rho 1. And this is 1 by gamma CS1 square by U1 is equal, plus U1 is equal to 1 by gamma CS2 square by U2 plus U2. U1 minus U2 is CS2 square by gamma U2 minus CS1 square by gamma U1. Which is again similarly on half U1 square plus gamma by gamma minus 1 P1 by rho 1 is equal to half U2 square plus gamma by gamma minus 1 P2 by rho 2. So this then again becomes half U1 square plus 1 by gamma minus 1 CS1 square equal to half U2 square plus 1 by gamma minus 1 CS2 square. So equal to gamma plus 1. It should be this CS1 square is again lambda square gamma plus 1 by 2 minus 1 square. This CS2 square is this. So we'll get that from here. You understand now from where you get. Here you have this conservation equation and you have this conservation equation. Remember CS1 square for this zone will be gamma p1 square by rho 1. Gamma is same because the fluid is not changed from monatomic to diatomic. It remains same. That's why. Shock jump conditions using equation for U1 minus U2 will be 1 by gamma U2 lambda square gamma plus 1 by 2 minus U2 square gamma minus 1 by 2. Similarly, this. So, okay, then this become U1 minus U2 lambda square gamma plus 1 by 2 gamma 1 by 1 by U2 plus gamma minus 1 by 2 gamma is equal to 1. So 1 by U1 by U2 is equal to gamma by gamma plus 1 by lambda square 1 minus gamma minus 1 by 2 gamma is equal to 1 by lambda. Which again on U1 U2 is lambda square and tail relation. Okay. So then you get this relation, Prandtl relation, that U1 U2 is equal to lambda square. This quantity lambda is very much interesting. You will see this is the constant that we have added. So then the shock jump condition again will get the CS square by gamma minus 1 plus C square by 2 gamma plus 1 by 2 gamma minus 1 lambda square. So we'll get this E1 square by lambda square gamma plus 1. From rho 1 E1 rho 2 E2 we get that rho 2 by rho 1 is E1 by E2. E1 square by E1 E2 so E1 square by lambda square. Using M is equal to E1 square by CS1 square. We will get that rho 2 by rho 1 is gamma plus 1 from here. This is the rho 2 by rho 1 is E1 square by lambda square. Okay. So put here. Okay. So we'll get rho 2 by rho 1 gamma plus 1. This is M square. And actually we need to divide by this term, right? So you'll get U square by C M square. 2 plus M square, here M square. And this is E1 by U2. So if we draw the graph here, if you draw the graph here, the log of ratio and the Mach number plot, will get that for rho 2 by rho 1, right? This will be the graph. Rho 2 by rho 1 with M1 will be this. Similarly, for V2 by V1, we'll get this. For P2 by P1, we'll get this. This is very important for this is for monatomic gas, which have gamma is equal to 5 by 3. So then, so also we have this. So then P1 by rho 1 E1 square, rho 1 E1 plus E1, this U2. So this is basically P2. Okay, P2 minus P1 will get E1 minus U2 times this rho 1 E1. Rho 1 E1 and rho 2 U2 is same. So you can interchange them. So P2 by P1 minus 1 is gamma E1 square by CS square, right? Because rho 1 is so E1. E1 is common, so E1 square. And rho 1 is gamma by CS1 square. CS1 square is gamma P by rho, right? And we have common here P1. So rho 1 by P1. So we have this. The simple calculation you can do it. I think you should do it. Your homework. So P2 by P1 minus 1 is gamma m square. This is again m. 1 square by 6 1 square. 1 minus 2 plus. We have put this equation u2 by u1 is 2 plus m square gamma minus 1 by m square gamma plus 1. So we'll get this. So P2 by P1 2 gamma by gamma plus 1 m square minus 1 plus. Basically, the idea is to represent in terms of the ratios. Ratios of P, ratios of rho, ratios of U. You can see na P, rho, U, and T also there. Right. So the idea is this. Again, we have done this for temperature also. So we know rho P is equal to rho RT, right? P is equal to rho RT from NKT, rho RT. So T2 by T1 is basically P2 by P1 rho 1 by rho 2. So let's put the ratio equation. All are functions of Mach number only. Okay. Transonic flows and application. Continuous transition of subsonic to supersonic fluid. Consider flow cross section changing. Steady fluid. Mass continuity equation rho AU is equal to constant 1 by rho d rho dx plus 1 by u du dx plus 1 by u du dx is equal to 0. Our equation says that rho del t plus rho u dot grad u minus is equal to minus grad p. So rho u du dx plus dp dx is equal to 0. Rho u du dx plus ch square du dx is equal to 0 minus u by ch square du dx is equal to 1 by rho d rho dx. So using in previous equation 1 by u minus u by ch square is equal to du dx is equal to minus 1 by a dA dx. The flow cross section changing. So then again transferring flows and applications will get basically transfer flow is continuous transition of subsonic to supersonic flows. So the cross section changing. Mass content equation there or equation there. And previous equation will get this. The area is changing. See dA dx. Okay. So this flow application is 1 by u m square minus 1 m square minus 1 du dx because cs u by cs square is m square equal to 1 by a du dx. So this relates flow velocity changes to changes in flow cross section correspond to a certain flow. You can see, right? If okay, I will explain in a bit sometime. Since u a greater than 0, u greater than 0 because velocity can't be negative. A is also greater than 0 because area can't be negative. So subsonic flows above the flow is now subsonic. Subsonic means m less than 1. So this side is negative. Okay, we'll get this side is negative. So then dx is next area is decreasing. So subsonic flow accelerate in converging channels, and suppose area is decreasing. Okay, so as area is decreasing here, A is decreasing, dx is decreasing. So then it will accelerate, whereas supersonic flow decelerate. You can check here. Suppose from here Mach number is less than 1. This side is negative. This side has to be negative. So A can't be negative. So dx is negative. So area is decreasing. Okay, and when area decreases, then at some point A decreases, decreases, is decreasing. This means M is M has to increase now. So M increases as area decreases, so speed will increase. Some point M will be 1. There will be some trans point. Okay, so then So let's head on to the next section, the disk accretion. I previously talked about the disk accretion, the cylindrical coordinates, quasi-Keplerian orbit. A gm by r square is mv phi square by r, or Vr much less than v phi. So the mass conservation del dot del T plus del dot rho v is equal to 0. This holds. Del dot del T plus 1 by r del r r rho v r plus 1 by r del phi rho v phi is equal to 0. Del T integration of rho dz, so this will be 0. So you can see the circulation, the accretion of in falling mass over this cylindrical coordinates, right? So so then we see that so then similar to this we see that the del dot del T plus del dot rho v is 0, the mass conservations, and from here we get for the cylindrical coordinate del dot del T 1 by r is for the rho v 1 by r del r of r rho v r plus 1 by r del phi rho v phi. This will be 0, and this is a cylindrical symmetry. And then this equation will be 1 by r del r of r integration of rho v r dz from minus infinity to plus infinity is 0, taking integration on both sides. So assuming no stratification of fluid over cylinder, no variation of radial velocity to z steady state, 1 by r del r of r rho v r to h is equal to 0, m dot is equal to minus 2 pi r rho v r dot to h, r rho v r h is m dot by 4 pi is equal to constant. So minus 2 pi r rho v r to h is the accretion rate, mass plus rho u, total mass accreted is rho u times L, right? So rho u, the area for a cylinder is 2 pi r times 2h, right? This will be minus 2 pi r rho v r 2h. U divided by vr. So momentum conservation, then again for statistical, so we will get that rho u times grad u is equal to minus grad p plus rho g. Along z we will get 1 by rho d rho dpz dz is equal to gz is equal to grad phi at z del z is of gm by root over r square by z square. So we will get at r much greater than h this. So along z we will get this along with the higher order terms. So momentum conservation for steady state accretion will be this, that 1 by rho Ez by h is equal to minus dmh by r cube. So we'll get the rho c is square, h is equal to cs root over r by gm times r. So this is gr by v phi. So h by r is cs by v phi. For a thin accretion disk, fluid has to be very supersonic to be stable there. Along radial, using the grad of a dot b, we know this is the vector formula. For more reference, please see my mathematical prerequisite video. You have a clear idea. We have u dot grad u equal to grad u square by 2 minus u cross curl of u curl of u is equal to 1 by r hat, r theta hat, z hat, del r, del theta, del z, u r u theta is 0 equal to z hat by r, del r u theta minus del theta u r, z hat theta by r plus del r u theta minus del theta u r. This u square is equal to u theta square plus u r square. Momentum conservation expression is rho u dot grad u is equal to minus grad p plus rho g along radial. So u cross curl of u is u r u theta by r plus u r del r u theta minus u r del theta u r of r cross z hat plus u theta square by r plus u theta del r u theta minus u theta del theta u r is theta cap cross z cap r hat. Thus we'll get this equation. Moment of conjugation with steady state equation will get that rho u dot grad u is equal to minus grad p plus rho g along radial. Substituting in momentum equation will get neglecting this term that u r del u r. So similarly del r u r square is order of u r square is approximately 0. We will negate this term. Consistency for quasi-Keplerian intersection. The more Keplerian the orbit, the smaller the radial velocity. Along azimuthal component v phi is root over gm by r. M is the mass of black hole accretion. So we'll get a differential velocity due to gravitational forces, shear forces, drag, viscosity, and dissipation. And then this heats up and radiates. Specific angular momentum v theta r is equal to root r. Any momentum lost to accrete via viscosity. So momentum lost will be happened via viscosity force. Then these terms will come. Again, the quasi-Keplerian orbit will get this. Tr theta will get some big term. I'll share these notes with you. So main thing is the energy distributed by viscous force is d. That is 3 by 8 pi dm dot by r cube. The equation is enabled by viscosity. It is equal to 2 by 3 m dot by h. Equation time scales are smaller than EP renormalization time scales. 2 temperature plasma is collisionless P can exceed H. The 2 temperature plasma. Later we need these kind of things for model. Shocks and particle acceleration. Thermal particles assigned to temperature determines distribution. This is the distribution formula. This is the standard Maxwell-Boltzmann distribution. Particles can be boosted by non-thermal processes. Shock improves the thermal population. Non-thermal deaths, power law fall-off for non-thermal population, that is n proportional to the minus alpha. What can cause such a distribution? Inelastic collision in a region with scattering centers, weakening charge particles, etc. After K collision, U is equal to beta to the power k E naught. N is equal to n naught p to the power k. Shocks and particle acceleration is equal to n naught by e to the minus alpha. This larger number of scattering, high energy, lower population, low approaching collision, the opposite catching up collision. So diffusive shock acceleration will be the DSA, the important phenomena. Diffusive shock acceleration. Left time shock moves at velocity u. Assumes SCs in both sides of shocks. In shock frame, this is the post shocked. The shock front propagate this side is the pre-shock. VSU V2 U by 4. In pre-shocked fluid frame, this is the post-shocked shock front, pre-shocked V10 because we are seeing from the pre-shocked frame. And it is now going, this fluid is this side. Because V2 is now 3 by 4 U. Because V1 is 0. Okay, earlier V1 is U, so we are seeing that it is going to U by 4. Because it is more, so you will see that it will coming towards us by 3 by 4 U velocity. Diffuse shock acceleration is approaching collision test particle gain energy. Some of these energetic particle diffuse in post-shocked fluid frame. Post-shocked is V2 is 0, test particle shock front pre-shocked V1 is equal to 3 by 4 U scattering center. Let's return to the sample problem, assignment problem. Correct option, conjure spherical accretion onto the compact astrophysical object in the polytropic index of the accreting Siemens constant shock formation is not possible. Is right or not? Same shock formation is possible. Equatorial surface around the compact star, the central object for a binary star system sustaining an accretion is perfectly circular. The Lagrangian first Lagrangian point is situated on the innermost equipotential surface of a compact binary. So you can see that the spherical accretion and compact the polarity index of the accreting gas remains constant. The shock formation is not possible. And the first Lagrangian point is like the Aditya mission. The first Lagrangian point is in between the Earth and Sun. So innermost equipotential surface of a compact binary. So right options are A and D. Question number 2 is consider the gas from a large star being accreted by its compact companion through a quasi-Keplerian accretion disk. The accreting gas has some initial angular momentum. Accretion can proceed even if the gas particles in the disk have zero radial velocity. A gas particle in this quasi-Keplerian accretion disk with a finite accretion rate will have a small inwardly directed radial velocity. The specific angular momentum per unit mass of a gas parcel in a quasi-Keplerian accretion disk at radius r1 is greater than that at radius r2 if r1 greater than r2. The specific angular momentum per unit mass of a gas parcel in a quasi-Keplerian accretion disk at radius r1 is greater than that at radius r2 if r1 less than r2. So we'll have that option B and C are correct because a gas parcel option is correct because for a quasi-Keplerian accretion disk there must be non-zero radial velocity of the infalling gas. Otherwise there will be not be any accretion. The specific angular momentum for such an accretion is proportional to root r. Option C is correct. B and C are correct option. Consider steady state quasi-Keplerian accretion disk around the compact object. So choose the correct option is the angular momentum per unit mass of a gas particle over the energy in the center of the compact object root r. And second option is just proportional to r. Turbulent it is envisaged in the Sakura-Tsunae prescription will be subsonic. Sakura-Tsunae prescription the visco turbulent it is can be supersonic. Option is correct as we discussed earlier. It is proportional to root r. The angular momentum about the origin of the cylindrical coordinate system about the compact object is proportional to root r. In a Sakura-Tsunae viscosity prescription, the speed of the radius cannot exceed the sound speed, which is why alpha less than 1. So option A and C are correct option. Consider a thin quasi-Keplerian accretion disk with a constant m dot. The dissipation rate per unit cross section at a certain radius r1 is d1 and at another radius r2 is d2. So d2 is equal to 4 d1 if r1 is equal to 2 r2. d2 is equal to 2 d1 if r2 is equal to 2 r1. d2 is equal to 8 d1 if r1 is equal to r2. The disk height 8 is proportional to r to the power 3 by 2. Okay. So answer C and D will be right option because the viscous dissipation rate per unit area is given by dr 3 by 8 by gmm dot by r cube. So it is clear that option C is correct. We know that for a thin disk is hence option D is also correct. We already have discussed all of this. I am just recapping for your satisfaction. Correct statement: viscous dissipation primarily hits photons with an exchange energy with electrons. Directly hits electrons. Sakura-Tsunae prescription: the viscous stress can exceed the gas pressure, cannot exceed the gas pressure. So option is correct because viscosity being a momentum-based process acts preferentially on the heavier species because it's a momentum-based. So higher photon has the higher mass. So by definition, alpha less than 1, the viscous stress can never exceed the pressure. Okay. So these are the all questions. Let's move to the next. Some two more questions. Accretion disks are formed when gas supplied with some initial angular momentum forced to accrete onto a massive central object. Pick the correct statements regarding disk accretion. A gas parcel in a quasi-Keplerian accretion disk with a finite accretion rate will have a small inwardly directed radial velocity. A gas parcel in an accretion disk with a finite accretion rate can have an azimuthal velocity that is equally exactly to the Keplerian value. The specific angular momentum per unit mass of a gas parcel in a quasi-Keplerian accretion disk and radius r1 is greater than that at radius r2. R1 greater than r2. The specific angular momentum per unit mass of a gas parcel in a quasi-Keplerian accretion disk at radius r1 is lesser than that at radius r2 if r1 greater than r2. So option A and C are correct because option A is correct since there needs to be a radial velocity for accretion to happen. M dot proportional to R rho VR H for a cylindrical shell of height H, where rho is the mass density and VR is the inertly. So you understand that the azimuthal velocity is Keplerian. So and we already denote is root R. Option A and C are correct. Correct statement. Again, similar question already come across this. Shear viscosity in accretion disk enables gas parcels at large radius to lose angular momentum. They are falling out. This is correct by definition. Option C, option B is option C. Let's see. Two compact objects A and B have accretion disks around them. The compact objects are equal in mass, and the rate at which the gases feed into the respective accretion disk at the outer radius is the same. If you think about the same coefficient kinetic viscosity, the gas is significantly higher than velocity of space more than B. I studied option C of the previous question. The specific angular momentum increases in increasing radius. So it needs to be lost in order to gas to settle to accurate. Option B correct because dissipation goes into hand with the viscosity. Radial involved velocity. When you kinetic viscosity coefficient, option D is correct. Assume that the local disk height in an accretion disk is proportional to the local radius. Is proportional to R. The accretion rate is constant throughout the day. It doesn't vary with radius. Assume the radial velocity is proportional to R minus P. Pick the correct statement. If p greater than 2, the gas density in the accretion disk will decrease with decreasing radius. The density closer to the center of it is smaller than that further from it. P less than 2, this is follows. So option A is correct as m dot is R proportional to R over H. If proportional to R, this becomes m dot is equal to Kr square over R. So K is a constant. If VR proportional to this, the rho will have to increase within R in order to keep m dot constant. When we have seen this, is said rho is equal to rho naught R to the power Q. M dot doesn't depend on R, so Q is equal to P minus 2. Positive number. Let's hold on to here sometime. So this we say we discuss about this. We discussed about all the. We can discuss it about this. So some questions in dealing with the adiabatic expansion phase of supernova shocks, we have used a self-similar variable J, which is a unique combination of the spatial variable R and time t. It is proportional to R and proportional to 3 minus 2 by 5. Is the correct option. Transform to such a self-similar variable enables us to work with a set of coupled ordinary differential equation instead of coupled Maxwell differential equation. Self-similar solution will allow us to specify initial boundary conditions separately in R and T. Variable J x plus Vt can be similarly for the one-dimensional wave equation, and this one-dimensional wave equation is option A is true. Self-similar because they also shown and is shown in class. A set of coupled PDEs does reduce to a set of coupled ODEs. Option B is not true. This is the main disadvantage of working with self-similar solution. Okay. There are no scales, specific values for RRT. So to speak, everything is self-similar. There is no meaning for boundary condition. Option C is true and D isn't. Such can be verified by substitution. Number 2, consider the false color image of Tycho supernova remnant at radio frequencies shown in figure 1. Most of the radio emission seems to be concentrated in the roughly circularly with the correct statements. And this is the figure 1. The Tycho Brahe supernova false image. Roughly circular ring. Radio emission, the red. Also the intense radio emission. This is the like empty core. So correct estimate, the picture seems dark inside the ring because the gas there is cold. No. The gas inside the ring cannot be cold since it has been subjected to the shock. It seems dark because there is negligible emission at radio frequency. It might be bright at other frequency. Yes. Gas will be hot. Radio emission mostly traces non-thermal electrons and is not very sensitive to a thermal population. X-ray image, for instance, would fill up the ring. Okay. The bright ring traces electrons that are accelerated by the supernova shock. This is true. Discussed in class. Okay. In fact, supernova shocks and shocks in most astrophysical settings, for that matter, are invoked primarily to explain the presence of accelerated particles, electrons in this case. Okay. The ramp pressure density times square of shock velocity. Ramp pressure density rho v square. Just inside the bright ring will be higher than the gas pressure or outside the ring. So it is in the lecture in fact the gas pressure outside is neglected. So ramp pressure will be there, so its pressure will be ramped onto the atmospheric pressure, the ambient pressure. We have seen that the location R shock of a supernova shock, always R shock proportional to 3 over 5 in adiabatic energy conserved. Okay. In the correct statement, this means that the shock velocity increases with time. This means that the shock velocity decreases with time. Shock is propagating with the constant velocity, and the shock is stationary. This shock is equal to dr shock by dt proportional to 10 to the power minus 3 by 5. The correct statement regarding aerodynamics. The B shock is equal to dr shock by dt proportional to the power minus 3 by 5. So right option is B. Decreases with time. In the correct statement regarding MSD, individual particles, electrons, protons cannot be accounted for in MSD. Yes, at macroscopic length scale, the fluid we describe with image does not carry any net charge. Image is a fluid description. There are no particles in the description. By definition, image describes phenomena at macroscopic length scales and slow time scales, so that the fluid is electrically neutral. Currents in MSD arise only due to the curl of the magnetic field. No particles, no question of there. So, no question of the fluid describing the current. As described in the lecture, the fluid in the image approximation is infinitely conductive. So there are no electric fields in the fluid. as per an observer immersed in the fluid. The study of immediate approach to hydrodynamics is relevant for stability because hydrodynamics cannot account for electric fields. Hydrodynamics is only for neutral fields. We need to understand this magnetic fields which are prevalent in most astrophysical scenarios. Hydrodynamics doesn't talk about the magnetic field. Much of the emission from astrophysical objects is due to accelerated particle radiating in the presence of magnetic field. That's because of it. At least in the fluid frame, energy also deals with neutral fluids. And we are in the only so yeah, these are the pictures. So yes, then magnetic currents using E is equal to minus B plus B by C, and D plus B is this. The curl of B there have no sourcing for ionized fluid. From continuity equation, d rho dt is 0 plus minus neutral and not due to charge particles of plasma. Then why curl of B evolution is determined by flow but exists due to B fields. Current force on the fluid is F L is equal to 1 by C J plus B. This curl of B plus B by 4 pi add force to momentum conservation equation, two equation, two variable, VB induction equation, P del T, momentum equation. Recall that P divergence of pressure tensor. Momentum equation of B fields is this integrating over volume minus head of minus integration of del dot M dB is equal to circular integration of N dot M ds. This is the magnetic portion B line parallel perpendicular to B. Balance again minus grad P to get direction of the components. If B flux increases, B square curve acts are outwards minus B by P x. X anti-parallel to B. Resistant to deformation like rubber bands, relevant for card flows when flux lines are squeezed. So B square by 8 pi. Magnetic buoyancy concept fluid emerge in deep field lines. Is equal to minus del dot M2. Group P plus B square by 8 pi del I 0. Del dot M2 dv 0. See the PIB is not symmetric perpendicular to surface with the magnetic buoyancy. The region of high P, low P, low density for some temperature, plasma beta is dependent. These are magnetic pressures, nothing about which term contribute most in QM. Force free convex is this. Glass freezing for perfectly conducting fluid. Only briefly lines are frozen over the flow. Surface area, line event. So then del phi will be I1 plus I2. Ionic change due to loop position change due to change in B. So this is conjugate. B field lines are frozen with the flow. With this process. Kinematic dynamo theory is consistently explain magnetic field growth for sustenance against resistive decay. Solar dynamo, the omega alpha model. Solar cycle change probability over 22 years. Differential equirotation, differential rotation period at different latitudes. Fastest at equator, slowest at poles. Omega hypotenuse directed fields wrap around the sun and get a geometrical component due to flux freezing. Solar dynamo, the omega alpha model. Alpha effect is plasma radially convected outward. The police for twist the flow as it expands outward and drag along the twisted hemisphere direction of toroidal field lines and thus giving some twist that refuse to keep toroidal field back. Alpha effect, omega alpha model. this poloidal field line. These are poloidal field lines. Okay, this is the axis. It is rotating. The differential rotation in equator and polar shift these poloidal field lines, make them toroidal field lines. This is the omega effect. Twisting of the field lines, toroidal field lines, magnetic loops, toroidal field lines, alpha effect. Ampere's law series units is toroidal field lines. We column B. Current density J in image D, usually written as 4 pi J is equal to C column B, implies that the plasma velocities in image D have to be non-relativistic. There is no restriction on the plasma velocity, it can be arbitrarily equal to C. In image D always divergence free, divergence of the current density is always zero. Current in image D can have finite divergence, which one is this? So you know A and C. Plasma in image D have to be non-relativistic. Current in image D always divergence free, still always zero. Correct option in ideal image, the electric field measured by an observer moving with the fluid is always negligibly small. Ideal image D, magnetic field measured by an horizontal is correct. So in ideal image, the electric field measured by an observer moving with the fluid is always negligibly small because the electric field is very less. Ideal image, in ideal image, the current density has neither a source nor a sink. And you are correct. Consider a cubical volume element containing a Z hat. Greater magnetic field B is equal to B naught Z hat, or B naught is a constant. Select the correct option. There will be no Lorentz effect on the volume element. The volume element will experience a finite Lorentz effect. It is not possible to say anything. The Lorentz effect on the volume element from the information given. The volume element will experience an infinitely large Lorentz force. So option A, there will be no Lorentz force on the volume element. Choose the correct option for a given boundary condition of potential. So potential magnetic field and configuration at the highest energy from all possible configuration that satisfy the boundary condition. It is not correct. For a given boundary condition, potential magnetic field configuration has the lowest energy. From all possible configuration satisfy the boundary condition. If the boundary condition, if the magnetic field is in a non-potential configuration, it will turn to less than finally at a potential configuration. So option B and said by. So I think you have understood problem. But then again, So yeah. So we have seen for this, so B and C will be the right option. Moving on to the next. For the next one, we have the self-similar solutions for the waves in MSD, the sound waves. So the consequence of compressibility characteristic is speed for small perturbations. That is C s square is del P by del rho and non-dispersive. So sound wave are basically the slams on a basically atmosphere or in MSD, the hydrodynamics. We don't consider them particles or rather the fluids or gaseous particles. So the slam into them. So the longitudinal wave are basically the sound waves. In presence of magnetized background, we have rho plus del rho, P plus del P, beta plus del V, V. With B is the B jet hat and del OH is 0. So if we linearize the mass conservation equation, momentum conservation and induction equation, we have del del T of del rho plus rho del dot B 0. Momentum conservation, we have rho del V dV dt and these equations. So basically the waves in MSD give this magnetic induction equation, which are the limit of del del T of delta B is curl of V cross B. Splitting into component, the continuum momentum conservation equation will give this matrix that curl of delta B, and we'll have this waves in MSD rho delta Vx is this, and rho delta Vy, rho delta Vz in XYZ dimension. And splitting into components into the induction equation, we have this B cross B and curl of B cross B, and this vector vector terms, several vector terms. This is becoming more complex. Uh, Please read upon this. I will share this document and make sure you read and phrase this properly. Writing y component and second order decoupled equation, we have non-dispersive wave equation that omega square is kz square v square, and we have this Alfvén waves. So Alfvén waves is velocity and B field when the perturbations are transverse waves, and the direction of propagation is along the magnetic field. Then the characteristic speed we have is to correspond to B square by 4 pi rho. So that is magnetic pressure divided by density. This is independent of compressibility. It does not require delta P and P. So wave in MSD, the magnetosonic waves, the exact components in Fourier space. We have mass conservation equations. We have Fourier transform in this XYZ, the imaginary number of particles equations, and the waves. In MSD, we have the two-dimensional matrix term and non-trivial solutions gives this the phase velocity as omega by k, and then we have with respect to the cosine square theta term. Then we have the dispersion relation in terms of the velocity and omega square by kx square plus kz square. And we have these terms plus minus are the fast and slow magnetosonic waves. They're non-dispersive, and isotropic group velocity differs from phase velocity by these terms. Okay. So for sound speed much greater than VA or VA much greater than CS, we have for magnetosonic waves traveling nearly perpendicular to VA. Fast mode isotropic, we have these equations, wave equations. Please read upon this. These are the node points. And for theta to pi by 2, you can calculate them, how these plots are given. This is the fast mode, alpha mode, and the radars are the slow mode. Then again, we have this and fast waves, almost isotropic, and slow waves are anisotropic, greatest along the magnetic field, which is P by B square proportional to C square V square. Shocks in MSD develop in MSD when U greater than CSVA, CFMS, and CSMS. Mass flux conservation when rho U, this is the tensor product, is 0. Momentum conservation, the Lorentz force and magnetic force along. And the shocks are classified by direction of B with respect to shock surface. Parallel shocks are when B along N hat. All the jump conditions same as hydrostatic shock. Del dot B 0, B parallel 1 is equal to B parallel 2, B1 is equal to B2. Perpendicular shocks are when B perpendicular to the normal. Then the flow energy Can convert to magnetic energy since B is discontinuous across the shock. Then the magnetosonic shock with root over B square plus C S square. These are the oblique. So there are another type of shock that is called oblique shocks. B at angle of a B when the B is some makes some angle with the normal to the surface, like some angle theta or phi. Then the post of B is bent away from the surface normal, so that it is called a B tangential increases in FMS. And towards in hand, the B tangential decreases, and then we have the B increases post shock. That's how the shocks are in the sense of supersonic or subsonic. Some sample question will be correct statement. The wave propagation vector is perpendicular to the direction of the velocity perturbation. Wrong. Wave propagation vector is along the direction of velocity perturbation since sound waves are longitudinal in nature. The group and pitch velocity of small amplitude sound waves do not depend on the sound velocity. The sound waves are non-dispersive, the velocity is frequency independent. Choose the correct options. Plasma meter denotes the ratio of the magnetic pressure to gas pressure. Wrong. The plasma meter denotes the ratio of gas pressure to the magnetic pressure. And then the plasma meter proportional to C square B square where C is the sound speed, B is the Alfvén speed. Okay. The next one is the concept two system A and B. The magnetic pressure in A is twice the magnetic pressure in B. The density and temperature in A and B are same. Choose the correct option. Then the Alfvén wave of system A will be root 2 times of that in B. The sound speeds in A and B will be equal. Okay, from the definition. Correct statement: slow magnetosonic waves become almost iotropic when the Alfvén speed is much larger than the sound speed. When C is much greater than Vs, slow magnetosonic waves propagate at a speed that is smaller than Va. And when C is much greater than Vs, slow magnetosonic waves propagate at a speed that is similar than Cs. Primary shock is the right option. The mass fluxes on either side of the shock will be equal. The magnetic stress needs to be taken into account in considering the conservation of momentum flux. Other options will be wrong. Choose for correct option. For a fast mode oblique image shock, the B field is refracted toward the shock normal. For a slow mode wrong, for a slow mode oblique image shock, the B field refracted towards the shock normal. Know that for a fast mode oblique image shock, the B field refracted away from the shock normal, and for a slow mode oblique image shock, the B field is refracted toward the shock normal. Know that this component of B parallel to the shock normal does not suffer a discontinuity. Finally, for a fast mode shock, mod B increases in the aftershock region. Option B and C are correct. Okay. Moving on to the next section, we will have the magnetic reconnection when the cutting and pasting B field configuration. Non-ideal MHD stress solar B field twist due to differential rotation field configuration relates to potential configuration. This is a kinetic heating. Operating ideal MHD due to flux conservation. Okay. This is the magnetic reconnection line. It's a cutting and pasting of the B field configuration. Magnetic reconnection happen. What is the direction of B in between? Smooth transition between two oppositely directed field lines. Current sheet flows into plane to generate such fields. Current sheet gets thinner as B field lines approach. Reconnection length scales. Finally, redistributive B flux violation allows reconnection. Annihilation and rate of reconnection. Non-ideal image is finite redistributive non-zero. For steady state, rate of B annihilation is rate of inflowing B. Plus due to redistributive effect, del B and del T is equal to lambda delta square B. Steady state condition, V I B not by L, lambda B not by L square, equal to B square, equation to non-ideal defects. Annihilation rate of reconnection is demanding incompressibility, mass conservation gives this. Demanding pressure equilibrium gives this. These are the some basic equations of annihilation rate of reconnection. Higher resistivity is non-ideal, larger reconnection rate. Reconnection rates depend on mass conservation, pressure equilibrium, steady state annihilation of B fields. In astrophysical situations with high conductivity, Vi less than Vi, but from indirect observation, Vi approximately Vi, annihilation rate of reconnection is caviar, single reconnection events, indirect observation, uncertainties, kinetic, microphysics. Possible resolution is pairs check reconnection, geometry of reconnection region, reconnection occurs over a smaller region, V is equal to L by L star V. Rate approaches, alpine speed of reconnection occurs over length is comparable to current state thickness. What are the astrophysical applications? Energy release in reconnection and reconfiguration. Release is coronal mass ejection, flare events in sun and active galactic nucleus, etc. Electric field in reconnection region accelerates particles. Coronal events are probably powered by magnetic reconnection, solar flares, and coronal mass ejections. Loop stretches, plasma flows, the trace diffuse lines, space weather transients. The sample problems are: what is the correct statement? Magnetic reconnection is usually associated with plasma heating. Magnetic field topology unchanged magnetic reconnection. Magnetic reconnection does not have any relation with plasma heating. Necessary changes in the magnetic topology. So you can guess the answer that reconnection is usually associated with plasma heating. And topology change, so it is wrong. Magnetic reconnection is associated with changes in the magnetic topology. Okay. During magnetic reconnection, magnetic flux is not conserved, magnetic flux is conserved, there will be a high electric field expanded due to the current sheet is proportional to the inflow speed. Magnetic flux is not conserved because magnetic reconnection destroys magnetic flux, and option is true. Option is correct because due to finite resistivity, there will be a finite electric field at the point of reconnection. The root of the current sheet is inversely proportional to the inflow speed. In the Sweet-Parker reconnection model, the outflow speed far from the X point is independent of the magnetic Reynolds number or independent by the density of the plasma. Let's take reconnection model. The outflow speed can see the local magnetosonic speed near the X point. Finite resistivity effects are important. Option A, C, and D. In the Sweet-Parker model, the outflow speed is essentially the Alpine speed, hence it depends on the density of the plasma. Option C and D are covered directly in the lectures. Options A, C, and D are the right options. Select the correct option. Auroras caused by geomagnetic storms are generally observed close to the equator. Coronal mass ejection are one of the primary drivers of space weather disturbances. Corona graphs are usual artificial electricity in order to observe the solar corona. Flares are another name of CMEs. So B, because this is the space weather disturbance caused by CME, and coronagraphs use artificial eclipses in order to observe the solar corona that basically block the solar photospheric emission. Choose the correct option regarding CME. CME expand as they propagate, often associated with solar flares or what? Yes, expand during the propagation. It can be seen in the videos. They are often associated with flares close to the sun. CME density is higher than the background corona. That is why you can see it. CME typically propagate speeds at a few hundred kilometers per second. So this is the options. And so we spend some time here. So these are the live session 12. I talked about magnetic reconnection, cutting and pasting different configuration. MSD I talked about. This is the forward and at a reconnection order direction of B in between. Smooth transition between two oppositely directed field lines. Flows into plane to generate such fields. In this annihilation rate of reconnection. Please read upon this. I will share this document with you. The sample problems is this. Magnetic reconnection usually associated with plasma heating. You know that. Magnetic reconnection is associated with changes in the magnetic topology. Magnetic topology are changed. During magnetic reconnection, magnetic flux is not conserved. Obviously, because magnetic reconnection destroys the magnetic flux, there will be finite electric field at the exponent. Yes, there will be finite electric field at the point of reconnection due to the finite resistivity, which the current is inversely proportional to the inflow speed. The Sweet-Parker reconnection model, the outflow speed are from the exponent independent of the magnetic Reynolds number. B is not right. In the pet reconnection model, the outflow speed can exceed the local slow magnetosonic speed near the X point and a resistive effect. Pause the ACD and the correct options from the lectures. Overall, Corbett geometry system as CMEs are one of the primary drivers of spatial disturbances, and flares are not another name of CME. This is wrong. Coronagraphs use artificial eclipses to block the solar photospheric emission. Regarding CME expand. Yes, they can expand in the propagation. They are often associated with flares. The CME density is higher than the background corona. That is why we can see it. It typically propagate at speeds of a few hundred kilometers per second. I think missed the earlier slides. The waves in MSD, the sound waves, so the slams of the sound waves in the main medium. This is some mathematical description or prescription. This is the waves in MSD. The loop, please read upon it. Shocks in MSD. The propagation vector is perpendicular to the velocity perturbation is wrong. It is the sound is longitudinal, so parallel. Group velocity is wrong. Do not depend on the sound frequency. Velocity is frequency independent. Does the plasma beta denote the ratio of the gas pressure to the magnetic pressure? B is correct. C is also correct. Consider two systems A and B. The magnetic pressure in A option A will be correct. The alternative system will be 2 times of that in B. And the sound speed in A and B will be equal. With the correct statement, slow magnetosonic waves option C is correct. When C is more bigger than B, slow magnetosonic wave propagate at a speed that is smaller than B, but a speed that is smaller than CS. Okay. The mass plus on either side of the shock will be equal, not equal. They are destroyed. Option is wrong. Mass plus on either side of the shock will be equal. The magnetic stress needs to be taken into account in considering the conjugation moment plus. Yes, it is right. Option C is wrong. The pre-shock mass plus will be larger than the post-shock mass plus, because the energy flux is not the same, but mass plus is same. The pre-shock momentum plus will be smaller than the post-shock momentum plus. For a fast mode oblique image shock, we field spread is wrong. For a slow mode oblique image, the field spread toward the shock normal. The component B perpendicular to the shock surface does not suffer discontinuity. And finally, for a fast mode shock, B increases in the aftershock region. Okay. So I think it's all here. So with this, we conclude more session. I hope most of this you have understood. From the next sessions, next two sessions, I will do some pen and paper kind of things that will help you understanding the assignments. I will do with my hand, my pen. Please be with me. I'll be there and upload those videos. If you have any query, please comment on the YouTube comment section or the group forums and refer to these. These are very important. The energy and the magnetic connection. Best of luck for your exam. Best of luck for your exam.
It's 1 o'clock.
Thank you for being there with me. Please keep up the good work and study and prosper. I hope I have been able to help you. Alhamdulillah. Okay, best of luck. Goodbye, good night. Sabba khair.